Tell me how you want your want it done. I just wanna please. All I wanna do is have your son. Well, yeah, don't tell me somewhere.
Anyway, great. Welcome everybody. This is amazing. Um, there are seats around. We just have to be creative. Welcome to the Creativity Museum. My name's Tim Gorman. I've been working with data warehousing for quite some time, and I can't seem to get away from this topic. So I apologize for those of you who've seen some of it before. I decided to get into a little more depth, I think, on the basic idea of using the exchange partition technique for data loading in data warehouse, because there's so much more than just the basic technique. It really deserves a little bit of coverage. I was conversing with one of the folks on the Oak table, and they had a particular problem with a data warehouse that they were building or helping repair, I think it would be a better way to say it. And anyway, she gave me the idea that I should probably rehash some of this again and go through it. So I wanted to talk, for those, how many people use Exchange Partition in their data warehouses for loading? Most of you. That's wonderful. There's a lot of variability. There's a lot of creativity and flexibility that can be used with the technique for a lot of different purposes besides just the basic loading. So I'll go through the basic 5-step technique and then talk about what I like to call the 7-step advanced technique or something like that for what I tend to call the dribble effect, because life is not perfect and data warehouses don't just load into single partitions at one time. And then I wanted to also talk about using the exchange partition technique for accomplishing updates much, much faster, more scalably than you ever could with an update or a merge statement. Okay, I'm sorry, I just had to, okay. So the little thing in the middle there is kind of interesting. Okay, each one of them seems to have it. That's in different parts. Okay, so insert append, direct path load, what have you. The fastest way to load data into an Oracle database. The problem is that it's a horribly antisocial process. In other words, nobody else can be doing anything to that table, even querying for that matter, because you basically have to disable indexes while an insert append is going on. It's a horribly antisocial type of operation. So how to use it, how to employ it in your data warehouse. You basically have to quiesce it for a period of time, right? Not right at all. The other thing about insert append, besides being the fastest way to load data, it's also the gateway mechanism, if you will, for basic or deduplication compression that came available with Oracle 9i, and also for the HCC that's in the Oracle-based storage, the Exadata, ZFS, and Pillars. You have to use insert append, direct path. The basic compression, a lot of folks will say, well, big deal with that. I can achieve compression with the advanced compression option. Doesn't really help you a great deal with data warehousing, the advanced compression, if you think about it. With basic compression, the stuff that came out with 9i, the deduplication, it's not a very high degree of compression, but it's better than nothing, far better than nothing. I know with fact tables and such that I generally achieve anywhere from 50% to 25% of previous data volumes. Use whatever number you want to express that. That's 2x compression, 4x, what have you. But easily 25 to 50% compression, and that really does help when you're talking about, say, 150 terabytes of data warehouse storage. That compression has been around for quite some time, only achievable with insert append. And again, with Oracle 11g, Oracle came out and said, well, I've got advanced compression, and now you can use that with any type of operation, with regular conventional inserts, with updates and deletes. The problem with that is, and I'm just going to have to wave my arms in the air because I haven't prepared slides to really describe this, but with advanced compression, what is happening is that you're loading data into your blocks, and then there's a background process that comes along and compresses after you. So think about that. That does work rather well for an OLTP type system. You're packing data down so that you can insert more data into those blocks. But in a data warehouse type workload, what's happening? You're loading data into blocks, and then tomorrow you're going to load data into other blocks. And then the next day you're going to load data into those blocks over there. So the advanced compression come around, compress everything, but the blocks don't shrink. Your data files don't shrink, your segments don't shrink. You just have emptier segments and blocks and such. And then you happily go on and just keep inserting more data further on, and you just have empty structures. So advanced compression does nothing for you in a data warehouse environment, or at least most data warehouse environments. So the trick is to compress on insert with a data warehouse, because for the most part, that's going to be your only chance, a single bite at the apple, so to speak. So insert append is what we want to do, to use that form of compression on insert into the data warehouse tables. Or again, if you're using some form of the hybrid, where did I get that word? Hybrid columnar compression used with the Oracle storage, same thing. The other thing is that, as I mentioned, it's a horribly antisocial situation. It exclusively locks the table being loaded. How do we accomplish this? We don't want hours of downtime in order to do our loads, obviously. 24/7 is very much a reality, even for data warehouses, because we have multiple time zones, each trying to work their 8-hour day against the data. We have crazy power users throwing 24, 48, or 72-hour queries against this set of data. There is no such thing as downtime. So the basic 5-step technique then is to create a scratch table off somewhere, off stage, so to speak, somewhere. Do our loads into that, and then prepare the table. Once we've loaded the data, we analyze it, we index it, and then finally, as a last step, exchange it to publish it, essentially. Now the data becomes visible to the world. And during that time, at no point was anyone's query interrupted, even during the exchange, because queries that are in flight will continue to use the old segment unless you drop it or truncate it. Queries that were started after the exchange partition use, of course, the new exchange partition. So I'll do my best to illustrate this in PowerPoint. Right now I'm just waving my arms in the air and it's pretty tough to visualize, but that's the basic idea. Load into a scratch area and then find, for years, I don't know how long some of you have been around with Oracle, but for years we've tried to find a way to do this seamlessly. To load data somewhere and then publish it by switching a synonym or renaming a table or anything like that. Exchange partition is probably the most seamless way yet in order to do that, to switch those identities. So again, basic technique. I like to use an example, and again, I apologize for the little cutouts disturbing the text or so. But the basic technique, let's just say we're talking about a fact table. This is your classic situation where one of the types of compression that need append loads is really useful. So it's a fact table. I'll just call it transaction. It could be in any data warehouse, and it's range partitioned on a date. And it could be any date. A lot of fact tables have multiple dates, and now it becomes a real game as to which of these dates you're going to make your range partition key. Now, in a perfect world for an ETL programmer, I would say, make it this artificial date that I'm going to call load date. Make that my range partition key so that when I load my data in for the 25th of February 2014, it's going to go into a single partition that contains all that data. Load date. But the problem is that the end users aren't even aware of something called load date. It means nothing to them. So chances are good your fact table is going to be range partitioned on a date column like transaction date, posting date, depending on requirements and such. But the basic idea is that you want your fact tables or any of your partition tables to be partition keyed on a column that is being referenced in the SQL statement where clauses, so that you achieve partition pruning. So all that's kind of beside the point. We have a transaction table, it's range partition on a date column. I just decided it would be nice to hash subpartition it on a number column as well. The matter of the choice of choosing that is again, we want to use as a partition key a column that's going to be used in people's where clauses as a filter so that we can achieve partition pruning most effectively. So this is all part of a long story, how this table was designed, but this is the table that we have, composite partitioned. So to set up the scenario, what we're trying to do is load one day's set of data, the 25th of February. Now that set of data might actually, well, I'll get to that in a second. We're going to load that data in, and ultimately we're going to publish that data into a partition that's called 2014-22-25. So this is my rather pathetic PowerPoint way of trying to represent that. Over to the left, the vertical boxes are supposed to be the range partitions. The horizontal, smaller boxes inside them are supposed to be the hash subpartitions. Okay. Sorry, I tried. And each one of those vertical boxes is a day's worth of data, okay? So this is a time variant table called transaction. The rightmost box that's all pink is empty so far. So the basic 5-step mechanism involves having a procedure that now uses that rightmost pink, all pink partition that's currently empty, using that as a template to create a scratch table. I just happen to call it TXN scratch. So I've got a procedure out there on the web that does this, and you're all welcome to download it as a template itself. And it reads the data dictionary for that partition that you name, and it creates basically a copy of that table off on the side, and I just happen to name it TXN scratch. So the idea is that's the first step, create the scratch table. Same table space as the partition to be loaded, because very often you're going to have your partition table scattered across multiple table spaces, perhaps also named by date as well. So create your scratch table, same table space as the partition you're about to load. That's the first step. Second step, insert append from your data source into that scratch table. It's got no indexes on it. Everything will fly right in. Third step, gather stats on it, however you like to do it. Personally, I like to see, might as well, compute stats. We're going to have this data for quite a long time. We might as well get very good stats on it. Maybe even take the time to do it. Maybe we have the time for that, maybe we don't, but I like to see compute stats. Next step, looking at the base table again, use the metadata to create indexes on the scratch table for the local indexes. So again, I've got a stored procedure that does this. It's on the internet. Feel free to download and use it as a template. No warranty, but feel free to ask questions. But at any rate, use that metadata on the partition to be loaded to create indexes on the scratch table that match local indexes. So okay, we've now prepared the scratch table. Everything is ready to go. Last step is very easy. Alter table exchange partition. And now what happens inside the Oracle Data Dictionary is that what used to be a standalone table, a hash partition table, is now a partition within the other table. Just metadata gets changed. Data doesn't move. So it's just simply a re-identification. There's a caveat to that, of course. The main caveat to that is there's two things you can do during exchange partition that could end up taking more than just a few seconds of re-identifying metadata. The one thing is that there's a clause called with validation. In other words, it'll validate the standalone table that you're about to make a partition for any data that doesn't belong in that partition. It's up to you whether you let it validate for you or not. Personally, I'm going to trust, in many situations, I'm going to trust my ETL process. I've had control of the data. It's up to me to make sure that I load the correct data and then exchange it in. So with validation can take some time to scan and validate each row in the table you're about to partition. exchange. The other thing that could take time is if you have any global indexes on that table that you're about to exchange into, global indexes would then have to be rebuilt, modified. And that's an operation that can take a long time depending on the size of the partition that you're exchanging and the global index itself. All I can say is work like hell not to ever have global indexes. That's a bit of a utopian goal because sometimes you absolutely have to have them. But you'd be surprised how many times you can be talked out of it. And this is a topic for another talk, but unique indexes are way overrated. You don't necessarily need them. And I can talk you out of it. I can make a good stab at talking anybody out of a unique index. And maybe that'll take care of most of your global indexes. But those are the two things that make exchange partition a little bit more painful than it needs to be. So that's the basic 5 steps. And again, I just reiterated here the basic 5 steps. Okay. So that's a perfect world. And you're sitting there thinking, oh yeah, my ETL is way more complex than that. Granted, everybody's ETL is way more complex than that. So to move on, oh, and the other thing is I've been mentioning this store procedure. I've had it out there for several years. I've got newer versions of it, so if what's there, if you download it, look at it, don't like it, it's missing something. It's got quite a bit in it, but if it's missing something, or it's got some of the customizations I think I might have put in at some point or another, you know, give me a yell, send me an email. I've probably got a newer version out there somewhere already written. Again, just use it as a template. It's certainly not supported code. But it's really useful. Here's the other thing, too. Do encapsulate this stuff in a stored procedure because then, sorry, back up, then you can use it inside ETL tools. Most ETL tools during their loading have a preload phase and a post-load phase. And now when you're running your load, you point it at the scratch table instead of the target table itself. So I make it into 2 stored procedures, prepare and finish. Prepare is step number 1 to create the scratch table. That's all that store procedure does. The finish does the last 3 steps, the gather stats, the create index, and then finally the alter table exchange itself. So it does a lot of work. So that's the basic idea there. Okay, complications in real life. Here I am. It's just imagine you're on the 25th of February, 2014. You're about to load, say, 1 million rows of data, okay, into your fact table. The basic idea, of course, is that your fact table is partitioned on posting date. You know, it's a credit card transaction fact table. Posting date, it's partitioned on. But the thing is that on the 25th of February, maybe 95% of your 1 million rows are for the most recent day, 25th of February. A smaller percentage are for yesterday. A yet smaller percentage is the day before that. You get the idea. And I call it the dribble effect. You're dribbling in data over time. And then you've got about a dozen rows from a month ago that have to be loaded in as well, all part of the 1 million rows. Real life happens all the time. This is, I'm sorry, a bit of an eye chart, but what I'm trying to describe here is the setup of having an external table. I called it extern stage, EXT stage. It's a flat file somewhere that's got my 1 million rows of data that are supposed to go into the table today. So extern stage, the basic idea, and you don't this isn't actually supposed to be real actual code, but the idea is that you have a cursor loop that's going through the external table first as a scan, finding all the distinct dates to be loaded. These are aligned with your partition keys. So I'm going to loop 1 iteration for each one of my partitions. If the rows to be loaded are over a particular threshold, I call it n. You can call it anything. Just for illustration's sake, I said it was only 100 rows. Pretty low threshold. If we have more than 100 rows to load, go through the 5-step exchange partition process. Okay? In other words, in this case, somehow or another, we have to have a scratch table that's already got yesterday's data in it. Load my rows on top of that. And then gather stats, create indexes, exchange. Otherwise, if it's less than 100 rows, just do a straight insert straight into the table. Even that could be kind of risky with 100 rows. Think about having a table that has been compressed, a fact table that has 35, 40, 45, 50 bitmapped indexes on it, maybe a few bitmap join indexes on it. Think about how long it'll take to even insert 100 rows into that table. It's going to take a while. So this threshold might be surprisingly low. It might take longer in elapsed time for you to insert 100 rows directly into that table with all the compression and all the bitmapped indexes and bitmap join indexes on it. Might take longer for you to do that than to seemingly take the long road around. I wrote a paper on this where I described a situation I had. We have a conference in Colorado called RMUG, and I had some guests there. We went skiing afterwards. We went up into the mountains, went skiing. As soon as we went through the pass over the Continental Divide, Thursday night after the conference, 15 minutes after we went through, they closed the pass, slammed the door shut on us, which is a great situation on Thursday night. But come Saturday, when folks have to make the airport, then it got to be a crisis. So I had to drive someone to the airport on a Saturday. The way I should have gone is, again, up over the pass, straight down to the airport. Should have made it in 90 minutes. But, of course, the pass was closed. So there's an analogy behind all this. So I had to go all the way up, almost to Wyoming, come all the way back down, find the tunnel that was open. It took 7 hours, I think, and I got the guy to the gate, to the curbside of the airport 30 minutes before flight time, and he texted me, right at flight time that he had made it, The point is that the longest route is sometimes the fastest. Sometimes under extreme circumstances like that, but in cases like this as well. Okay, so we have about 1 million rows to load, and you're thinking, I have to somehow shuffle around 1 million rows, and it's faster than just simply inserting directly 100 rows? And the reason for that is again, think about all the things that we've done to the table. We've compressed it. We've put all these bitmapped indexes on, each one of which could have the speed of any manipulation that we do against that table. And then we've got 35 or 40 of the little buggers. So we've done things to our fact table that have made it extremely difficult to manipulate. This is very often the fastest. But we've also got ways to make it even faster. So this is where I take the 5-step technique and make it a little bit faster, because in this case, the initial step can be the hardest. Okay, so we've got the slide that I had before showing loading 1 million rows. 950,000 rows going into today's empty partition. No problem, that's easy. But yesterday's partition is going to get 5,000, 4,500 rows or something, or 50,000, I forget. It's already got 950,000 or 1 million rows in it, yesterday's load. I'm going to push another 50,000 on top of it. So that would mean that my scratch table isn't empty when I load it. It would have to have yesterday's data in it. What a pain in the neck. I would have to create my scratch table and copy all that data out of yesterday's partition. That would slow down my load. Instead, I'm going to say, let's leave it until after we publish the data and load as a final step tomorrow's partition. What? Okay, hold on. So same thing, 5-step technique. Create the scratch table, but now give it a name that means something other than TXN scratch. Give it a name with a date on it. Yesterday's date, or today's date, sorry. TXN February 14th, February 25th, whatever, 2014. Create that scratch table, load into it, analyze it, index it, and then finally do the exchange. But that's not all. Take one step further. Drop the indexes on the scratch table and load it again. So let's see what I'm talking about here. When we did this exchange, we took, it's not an empty table, I apologize. February 24th, the second in from the right, February 24th is what we're loading. And when I did my exchange, I should have done better naming on this. When I did my exchange, I actually took an already loaded partition and swapped it to the scratch table. I am describing this very poorly. I'm even going to modify the slides as I speak. My apologies, but this is going to be called, and this is an empty. Start over. Okay. Yesterday when I loaded my slides for the 25th of February, I did this additional 2 steps in order to prepare for today. Yesterday when I loaded, I did 2 last steps with my scratch table that at that point was empty. I dropped the indexes that came over from the partition table, because when I do exchange partition, I can also swap the indexes as well. I drop those indexes, and then I reload the data that I just loaded for today a second time. This is in preparation for tomorrow. Okay, so what I've got out there is a table called TXN and then the date, the load date. Now, tomorrow comes along. I load tomorrow's partition in. It's into an empty table, no problems. But now I want to load 50,000 or so rows into today's partition. If I just do a straight conventional insert into today's partition, I'm going to encounter all kinds of difficulties. I'm going to have the problems of modifying compressed rows and therefore expanding them. And I'm also going to have the problem of updating or modifying some 35 or 40 or 45 indexes, bitmapped indexes. Not good. So, left over from yesterday, I have a table out there, a scratch table already created, that already has the rows loaded yesterday. It's a mirror image of yesterday's partition because I went and did these additional steps. So today I come along, and I'm sorry, it shouldn't show empty. And my first step is to either create the scratch table or use the one that's already there if it's there. If it's there, I load today's 50,000 rows on top of it. Remember, that table has no indexes. I load my rows on top of it. Now I gather stats. Now I create fresh indexes on it. Now I do my exchange. And again, I'm going to reload. What I just exchanged was a partition that used to have yesterday's, that had yesterday's data in it. When I did the exchange, I now have that image, that old image, on the scratch table, and my new data inside my partition inside the table. So now I need to make them mirror again. To do that, I reload today's load of data again on top of the rows in that scratch table, and I wait for tomorrow. So I'm collecting all these scratch tables, one per day, one per load cycle, until there comes the point where I'm no longer needing to do this. So there's actually an 8th step involved, and that is to determine how long to retain those scratch tables. Sooner or later, you're going to want to drop them. As long as you're no longer using them for the exchange partition technique, or as soon as you're no longer using them, you probably want to drop them. Get some space back. And so you're done. And now if you come back to this algorithm, if you do need to load some rows into it, hopefully it's a small enough number of rows that it won't take too long. You're going to ruin a little bit of your compression. You're going to have to modify 35 or 40 indexes, but hopefully it's a small enough number of rows to not mess things up too badly. So that's the dribble effect. The other major issue that comes along in this load technique is that, as you can tell, it only deals with insert. I'm inserting new rows in. That works great for a time variant table, but what about my point-in-time image tables, such as my dimensions and such? Is there anything that we can do for that? One thing that we tend to find is that when we try to modify those types of current point-in-time type 1 tables, we find that the update or the merge operation takes so long that it tends to dominate the workload and extend your load window. Okay, so there's a fast way to do this as well. We can use the exchange partition technique to update data as well. And how do we do that? We use all insert operations, but we end up performing basically a merge. So the idea here is that we have, again, the same picture. but a little bit different in terms of operations. Same 5-step operation, but the second step of doing the data load, the query looks significantly different because we're going to union together the data that was just freshly loaded into the time variant table with the current image data and find the latest image in a fast fashion. And then exchange partition to publish it. So let's do a little bit of setup here. What I'm showing here on the left is another, a time variant image of a dimension table. When you think about it, a lot of people think of dimensions as being static, as being data that gets merged together, but not for slowly changing dimensions. Slowly changing dimensions are the ones, as the name implies, change over time. A people dimension, anything involving people, is a classic example of a slowly changing dimension. So the thing there is that we have to have a time variant image of that so that we're taking dimensional data from a point in time that matches the rows that we're querying from the fact table. We generally have to have 2 copies of such dimensions, slowly changing dimensions. We tend to need a current point in time image to find the latest data, but we also need to have the time variant data for a person as they change over time. For instance, myself, I've had an American Express card for God knows how long, several decades. Three decades ago, I was demographically, a much different person than I am today. I don't even want to discuss the ways in which I'm different, but the thing is that person from 30 years ago is still the same name, same person, same flesh, but the thing is that a whole lot from a financial and demographic and marketing perspective has changed about me. When American Express is querying their transaction database, they don't want to match the transactions from back then against the demographic image of me today. So in that sense, that dimensional data has to be shown in 2 different forms. The time variant that shows, the person that's evolving through the 3 decades, plus the person today, mainly for load purposes, to be perfectly honest. Type 1 static dimensions are generally used for loading new data as opposed to querying by end users. But at any rate, we need to keep this type 1 dimension here. So what I tend to do is I've got my type 2 time variant data on the left. My type 1 dimension is also a composite partition table, but with only one partition ever. I only have it partitioned so I can use exchange partition to load it. That's it. I'm not doing partition pruning, at least on the range partitioning. I have it shown here as hash partition for pruning purposes, for query optimization. But I've only got a composite partition just for doing exchange partition. So the same thing as before. I create a scratch table, account scratch. And I'm going to load it with the data that's currently in today's current account dim table. But since I just did a load of the 25th of February's data into the account time variant table, I'm going to grab that partition's data and merge it. So some of the data is going to be, let's set this up. I'm loading 1 million new rows again, just using the same numbers. 100,000 of those rows are new accounts. They're pure inserts. 900,000 of them are changes to existing accounts. They're updates. So the way you would normally handle this is a merge statement, like that. I'd merge into cur account dim, select from, God, I'm sorry, I did these slides very quickly. Let's go back to this. This is better. Yeah, I think I did that correct. Maybe I did. Yes, I did. I'm sorry. It's an early morning here, too. My merge statement has a select from the changed data, which is that 25th February partition. When matched, I do an update. When not matched, I do an insert. I'll tell you what, for 900,000 updates on a fact table that's compressed with 35, 40, 45 bitmapped indexes, that merge statement's going to take you all day, if not longer. It's going to take you a long time. Instead, if we do an insert like this into the scratch table, a 3-way inline view. The innermost red inline view shows us doing a select from the current static data, the entire 1 million rows that are in the cur account dim. Union all, select from the newly loaded data into the time variant table. That's however many rows. What was that now? I'm loading. Oh, no, sorry. Cur account dim is 15 million rows. Account dim that we just loaded is 1 million. So the innermost red subquery is going to be fetching 16 million rows. But we only want to keep 15.1 million. Because of those million new rows, we're loading 100,000 as fresh inserts, 900,000 updates. So in the blue subquery, we have a row number, which is like a ranking function. I like it because it breaks ties. Row number breaks ties. Ranking sometimes has several rows with the same rank. Row number over partition by the account key. That's our unique key, account key, in our static dimension. It's our surrogate key. Order by effective date descending. So we might have 2 or 3 rows for the same account key. I want the latest. So the middle partition passes through 16 million rows still, but it ranks them. The outermost query, the select that plugs into the insert, has the where clause of where row number equals 1. In other words, only the most recent effective date. So what we end up doing here is, yeah, we use up a whole lot of temp space. We use up a whole lot of query processing power in parallel, but we end up doing an insert append. So even our dimensions can be compressed. And dimensions also have an enormous number of bitmapped indexes on them on each attribute. They do have a B-tree index on the primary key, basically a primary key constraint, but they also have an enormous number of bitmapped indexes, which also make it terrible to try and modify them. So in this fashion, in many ways, the exchange partition technique in all its forms enables large bitmapped indexes. Because you know and I know, if you use OBI-EE, they drop all their bitmapped indexes, then they do their data loads, and then they create them all on each load cycle. Go ahead and keep trying to do that into the future when you start having terabytes worth of data. It's not going to work. So, merge upsert. So it can be done either one of 2 ways, using this merge command or the modified, the exchange partition technique. Okay. So in summary, my advice, load the time variant tables first, using either, if your load cycle frequency matches your partition keys, then you can use the basic 5-step technique. Chances are that's not the case. Otherwise, then you have to, you've got the dribble effect, you need to use the 7-step technique. Once you've loaded your time variant tables, then reload your type 1 static tables from that information. All of this can be done with insert, even though it's basically merge functionality. So it scales. It allows all the advanced features of Oracle for data warehousing, compression, bitmapped indexes, bitmap joins, star transformation. It's a wonderful thing. So there's a thank you. I've got a couple papers on this. They're a little bit aged. Sorry about that. But they're also very useful. And just wanted to mention our conference in Denver. If you want to come skiing, let me know. Snowboarding, want to learn. I don't know. I've taught a couple of the Okies how to snowboard. And tell me that's not good fun. So any questions? Do I have any time? Am I out of time? I'm sure there's questions. Go. I didn't even get into statistics. Yeah, the question was, I don't know if anyone would hear me, but don't you use incremental statistics? And the answer is yes. But I didn't want to talk too much about statistics here, except the basics of gathering partition level statistics at the moment. Yes, yes, absolutely.